Can you see my screen?
Yes,
Yes,
Doctor.
sir.
Yes. Okay. So you remember that last class we are discussing this slide and then we stopped the class. Uh, so today we'll be looking those details about braking register control. So, so the first one is you see that why nonlinear control for braking register switching? Why the nonlinear controller is needed? Why the or what is the issue with the conventional method? So you see, I have written that conventional method use fixed time and magnitude of control for braking register operation. As a result, these strategies are inflexible and are not adaptive to the changing operating conditions of the system. So this means that there are conventional methods available for braking register, but those are kind of fixed in terms of control magnitude and timing. For example, they can handle only a certain amount of power, or they can handle only, for example, 2 seconds or 3 seconds. In that way, those are designed. Therefore, so those are not inflexible. Those are inflexible and then are not adaptive to the changing condition. Changing condition means, for example, power grid structure might change, power flow might change. Again, you know that fault type is not the same always. It could be 3LG fault, it could be 2LG, it could be 2LS, etc. So that's why we need a method that can be adaptive to the changing situation. Now, nonlinear controller, just example is that fuzzy logic controller, neural network, any artificial intelligence method. Those are basically the nonlinear controller. And those work well in uncertain, imprecise, and nonlinear situation. So now I am highlighting the keyword nonlinearity. You see that power grid is highly nonlinear. I mean, we are discussing about the braking register. Braking register can be the linear component, but the braking register is connected with the nonlinear components, lots of hundreds of nonlinear components. Like generator itself nonlinear, all those line parameters or any inductance, those are the nonlinear. Loads are nonlinear. So therefore, power grid is highly nonlinear, that capital. And also the location and type of the fault in power network are quite uncertain. You don't know that when and at what location and what type of fault will happen. You don't know, all are like uncertain. Therefore, you have to choose such a controller that can work under uncertain situation, not the certain situation, not any fixed thing. If it is any fixed, known things, then definitely a linear controller will work better. But when there is uncertainty, impreciseness, and highly nonlinearity, then you need a nonlinear controller. Therefore, one of the best example is the fuzzy logic controller. And that is the reason probably you notice that I showed in several pictures. For example, here, fuzzy control device. So fuzzy control because that is the nonlinear control. So it can handle all uncertainties well. Therefore, to surmount or to overcome those drawbacks of conventional methods, nonlinear controller is needed or can be applied for braking register switch. Now, let's have a look on example of example power grid. Before I have showed you this diagram, for this system, let's analyze or let's apply the braking register, how it works. Now, you see this is quite complicated system. There are 10 generators like G1, G2, G3, G4 in that way up to J10. G10 has the highest capacity, 30,000 MVA, and then G1 has 15,000, and then the rest GT to G7 1000 to 1000. G8 is little smaller, 5,000, and then G9 is 10,000. And you see they are highly interconnected system, and the distance is maintained like 100 kilometer. I mean, although it looks like just a small line, but from this point to this point, this is 100 kilometer. From this point to this point, 100 kilometer. Like from here to here, that is also the, I think that is 50 kilometer. the connection point of this generator and this bus. So in this system, the braking resistor have been applied. So I'll be discussing one case. And can you see by red color, I have mentioned some point like point A, point F, and point G. So in fact, I mean, fault can happen at any of the location of this network. This point, this point, this point, this point. I mean, you can consider A to G, 100 points, no problem. But the reason I have shown, for this system, the point A is the most vulnerable. I think I have written it here. Fault point A is the most vulnerable for this system. Therefore, just keep in mind, for every network, every power system has a certain point in the among the entire points or among the entire buses. If the fault happen at that location, then that is the most dangerous. Therefore, for this system, this is the most dangerous. So therefore, why I am saying and what is the meaning of most vulnerable? Just look the picture here. System responses. In this axis, this is the time, and in this axis, load angle. This is one of the simulation result. And without braking resistor means no braking resistor was connected. This means there is no transient stability control means in that network. And then just the load angle was plotted. So you can see, because there are 10 generators like G1, G2, G3, we are looking the load angle. And can you see 3LG fault happened? Initially system was running fine at the very first. And then the fault happened somewhere around at this point. And then it goes a little bit up. It looks like it is coming down, but then it could not come back. And then again, it started much overshoot, downside much overshoot, next stage much more overshoot. I mean, growing oscillation, fully unstable situation, lack of the synchronization. This means fully out of state. So that's why it is called vulnerable. And it is not just like one or two generator, all of the chain generators went out of step. And then the next figure I am showing on applying with fuzzy control braking resistor. Now, if you connect the braking resistor that we are discussing, then you see initial pattern is the same, but from this peak, it has been controlled. Once you applied the fuzzy control braking resistor, then it came back, and there is some oscillation going on, but I mean, after some time, it will be settled down. Can you see the tendency? It will be, if you see simulation for 50 seconds or 100 seconds, then you can see it has been smooth. But here you see fully uncontrolled, not just stability issue, fully vulnerable. So, sorry, that is the meaning that for this system, point A is the most vulnerable. Even for this system, like I have some idea about this system, even for single line to ground fault, some of the generator goes unstable. Not all 10 generator, but at least 3-4 generator behaves like that for this system. It is so severe system. So why I am emphasizing this point? This means when, now here is the thing, you see, there are 10 generators, therefore it makes sense to put 10 braking resistor at each at terminal. For example, on braking resistor here, other braking resistor here, other braking resistor here, 10 braking resistor. But for economy purpose, it may not be wise to place all 10 braking resistor across each 10 generator. So you have to pick up some location, a specific location. You may need to reduce the number of braking resistor to save some cost. For example, this generator has 5,000. You may not put across it, but you have to definitely put one here, because as I said, this is the most vulnerable. This is the highest rated. You need to put one. And then, for example, you can make coherent group that you have learned before, that which generator behaves equally. So you make a clustering or coherent group. For example, this for one group, you can put one, and then this is another group, you can put two. Therefore, for example, 1, 2, you must need one here and then one here. So only 4 or 5 may be enough. So now if the system structure is more complicated, then you might need more. But of course, if you put one braking resistor at each generator terminal, definitely Stability performance is the best. Transient stability improvement will be the most. That is for sure. But that may not be economical. That's why I am saying where to put the braking register. Now, whatever we make analysis or not, coherent group or not, the point which one is the most vulnerable, there you must put on braking register, irrespective of any analysis, the grouping or clustering or whatever optimization technique we use to reduce the braking register. For example, for this system, it has been shown that by optimization algorithm, you put on braking register here and 3, 4 in this zone. And if you don't put anything here, again the system is unstable. I mean, that behaves like that. Even though you put the 9 braking register in those location, and if you don't put any braking register here, then still system will be unstable. That's why what I am emphasizing, for every system there is a vulnerable point, and that is the most dangerous point. You must put control means there. I mean, we are discussing braking register, that is okay. It can be some fault current limiter or some other device, any energy storage, any reactive power compensator. So for this system, you must choose point A. That is the meaning. So now the next question is that, okay, I put one braking register here, being the fact that that is most vulnerable. I put one here. The rationale is that it is the highest rated, and from optimization algorithm, I put, for example, one here, or let's say one more, so total 5. Now the question is, when we will be applying the fuzzy logic controller for that braking register, what should be my input? For example, before I showed you, probably you remember in other classes, that what was the input? Today, you see, I have written TKED. TKED means total kinetic energy deviation. Today, I have changed the input. I am going to explain why I changed this one. But maybe you remember until last class, I think last class and then other class, I put del omega, the speed deviation of the generator. Meaning that this is the generator, you are putting braking register across its terminal and then measure its speed and then take the speed deviation. But today, what I said, I mean, my output is the same, control input alpha, which will trigger or which will control the thyristor circuit. That is fine. But input is very important. Which parameter to use as an input? Today, I have used TKED, total kinetic energy deviation. Total kinetic energy deviation means it will take into account the effect of all the generators. Not just like I have put the braking register here. Not only I will put the speed information here, but I have to take into account all of the generators. Therefore, what can be that global variable or global input signal? That is the point of interest. So therefore, in this case, you know that because each generator is spinning, right? These all are the synchronous machine. So therefore, synchronous machine, they are spinning and they have a certain speed, and every generator you see it's huge, 15,000 MVA. So they have a huge mass. So therefore half J omega square, meaning that their kinetic energy. So therefore this generator has kinetic energy, this generator, every generator has kinetic energy. When any fault will happen at this point or any other point, each generator will be disturbed some way. This is the most vulnerable, but all other generators will also be disturbed. Therefore, at that time, you have to collect their kinetic energy. So therefore, basically, kinetic energy is half mv square, or we looked the equation before, half j omega square. So half is half, omega is the measured speed, and j is the moment of inertia. So therefore, that moment of inertia, you can calculate from that age value, like before we solved some problem few classes back. So therefore, you have to measure the speed from each generator, and you have to collect those signal, and you have to sum up here and make that difference. So that's why the input is total kinetic energy deviation TKED, W total. W total means total kinetic energy at transient state, means during fault situation, minus W total at steady state, meaning that during normal condition. where W total is the total kinetic energy. So therefore, you see in the, I'm coming back again. So in the next slide, you have seen how to calculate the total kinetic energy. So you all know this equation, W total, meaning that sum of I equal to 1 to n. N is the generator number. For example, for the system, there are 10 generators, your n value is 10. And that is the Wi, kinetic energy. What is the Wi? This one, Wi half Ji omega n square. You see, before we discuss this one, and what is Ji? That H multiplied by MV rating over this one. So therefore, fully we discuss this thing when we solve the problem of inertia. Therefore, you see, according to this equation, if you know the H value for a system and you know the MV rating, and then if you just know the E speed, then you can calculate the kinetic energy and then sum for all the generators. So therefore, definitely, you see that it is on generator here, I am showing. But those 10 generators are located at 10 different places. So meaning that when I'm putting on braking resistor control circuit here, then it is collecting the information from here. All of the generators are sending signal to that common controller. And then it is calculating that what is the total kinetic energy amount. And then it is comparing with the steady state value. And then if there is difference, then that is going to the thyristor. So therefore, what I am emphasizing by the TKD, you see, for multi-machine power network, multi-machine means when there are machine more than one. That is the definition of multi-machine. It is needed to use a global variable instead of a local variable as control input for braking resistor switch. Now you can argue that, so what is wrong in using the omega? I will take only its speed. Okay, of course that will work. That may not be optimal, or that may not be a trade-off or compromise for the overall system. If you only control its speed, if you take the input, then this generator will be controlled, but that may not have impact on those generators. So you have to use a global variable so that the contribution goes from all of the generators, and then that braking resistor equally contribute to each generator. That is the meaning. Everybody, could you follow me so far?
Yes, Dr.
Yes, sir.
Yes, Dr.
I mean, what is the necessity of having a global variable instead of a local variable? That is this point. Okay, so therefore you understood these things. So therefore, moving forward, now the couple of exercise question. You see that always I ask you questions. So today again you will face multiple questions, and then you have to write down the answer in your note. Now, to evaluate this type of big system, because we are studying the transient stability, I mean in this course. So to evaluate for this type of system, definitely you need a criteria. For example, you use the braking resistor, and then okay, it is controlling. So how do you understand that this system is working well? What is your criteria? What you will be looking? So definitely you can answer that. Okay, I will be running the simulation and I will be looking these profiles. Okay, that is the appropriate right answer. But as an engineer, as a power engineer, always we like to quantify. For example, I am saying that, okay, this result is better than this result. Then in this case, of course, because by visualization, it can be understood that, okay, these all 10 generators goes out of step and they did not. So that is the clear difference. But if the fault is other point, for example, at F point, G point, any other point, you might not see these results. Like it will be oscillating. They will also come back, but much more oscillating. Now, if you compare this result and with those results, then you might not see even much difference. So someone might argue, why are you telling that this is maintaining the stability? What is the criteria? How to judge that? Only you will be looking by eye and you will be telling, or there is some quantification system. So that's why I said as an engineer, we have to quantify everything, not just looking the plot. So therefore, this is one equation to evaluate the transient stability of a large power network for multi-machine system. You will be keeping this equation in mind. What is that equation? WC in second, and that W total, that total kinetic energy that we discussed, d by dt. This means time derivative. Why I am making time derivative? Because during fault, that kinetic energy is changing. So what is the rate of change? That is the meaning. And then I am taking an absolute value, and then dt, and then I am integrating 0 to t, and then I am dividing by system base power. So that's why ultimately the unit is coming second. Now this is one important equation to evaluate the transient stability for a multi-machine system. Now with regard to that, the question is, everybody see, the following equation depicts an index used for evaluation of transient stability in a multi-machine power system. And in the literature, it is described that the smaller the value of the index WC, the better the system performance is. So can you explain why the smaller index value means better performance? So this is the equation to evaluate the stability. But literature says the smaller the value of the index, the better the system performance. That is the meaning. So, for example, you are quantifying these results. You are quantifying these results. And then you got that, okay, you got in case WC 2 seconds, and other case you got WC 5 seconds. So the question is, why 2 seconds is better than that 5 seconds? Why the smaller value is better? So that is the question. So by looking the equation, can you tell that why the smaller value is an indication of the better performance?
May
Why
I
not?
try?
Yes, sure, please.
Thank you. I think maybe because when I get high or big power, the system-based power it bigger, I will get small number. So that depends on the value of the power.
Yes, of course, that is right because it is system-based power. But keep in mind that system-based power means, for example, this is a system. Look, this red portion, the base power is mentioned like 1000 MVA. That base power is
So it's
used.
constant. Oh.
Yeah, it's constant. So therefore,
Mhm.
for every system, like for example, for this system 1000, other system may have 5000 or 500 MVA. Different system have different base. So I mean,
Mhm.
of course, that is one factor that is influencing the equation. But or how about this portion in the
I,
equation? Yes.
so I think the lesser value of WC means like there would be less change in rate of like W total. That
Yes.
means like the rate of change would be very small. That means it is more stable. That's why the smaller value would be desirable, I think.
Yes. 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 So Amani, could you follow what he said?
No, sir, I'm sorry.
Okay.
Can you repeat, please?
Yeah, so therefore, I mean, you are dividing by a fixed system-based power, that is fine. But you see,
Okay.
it is d by dt w total. This means rate of change. This, and then you see, you are integrating. You see, 0 to t. Over the time, you are integrating. So, for example, you are integrating. Look, this one. For example, you are integrating from this point to this point, 20 seconds, or you are integrating until 10 seconds. So, therefore, whatever time you integrate. So therefore, when there is no difference, there is no change. That time this value will be 0. You see this one. In the controller, input was TKED. What is my TKED? Total kinetic energy deviation. How much it is changing? You see W total at transient state minus W total at steady state. Therefore, when you see when the generator, all generators are running, there is no fault in the system. You have a W total, right? Because this is your W total equation, sum of all the generators, kinetic energy, half GI WMI square. So when there is no fault, which Ji is moment of inertia, that is fixed because it has a fixed mass. Speed is also constant when there is no fault in the system, no disturbance. Therefore, you are getting a constant number. Therefore, your W total is a constant number, this thing. But once there is any fault, because generator speed will change, they will be increased. Consequently, your W total will be changed. So therefore, what is your goal? The goal is so that there is not much change of W total during the fault condition. Because there is change, that's why you are using braking resistor. So therefore, when you will be applying the braking resistor and then system response will come back in this position, I mean, they will match to the original values, meaning that that time your this difference will be zero. There will not be any difference. So that is what is expected. So that's why the question is, this is because d by dt W total, change of rate of change of W total. So this means if the change is lower, meaning that you will get a small number, you see, because you are integrating whatever time 0 to 20 second or 0 to 100 second, because you are looking rate of change. If there is less change, meaning that you will get less value. So therefore, because for example, braking resistor you used and it maintain the transient stability. Transient stability means your system response return back to the original value. So this means you will not get much difference. This value will be much smaller. Consequently, you will get less number. So higher number means, okay, there is difference between the transient value and steady state value. There is much more change in the system. Everybody, could you follow me?
Yes, Dr. Ali, I got it now.
Yes, yes, yes. So therefore, this is just by looking the equation. The lower the value or the smaller the value, better the system's performance. Okay, so the next question is that consider a power network faces the following faults: single line to ground fault, double line to ground fault, three line to ground fault, three line fault, and line to line fault. Now you would like to design a nonlinear controller for transient stability enhancement purpose. However, the controller has few parameters that need to be tuned. Whatever it is, fuzzy logic controller or neural network or other controller, you see, every control system has some sort of parameters that you need to tune. And only one set of parameter is desired. So there are few parameters that need to be tuned, and then you need only one set of tuned parameters. From the perspective of the mentioned faults, how would you tune the parameters to meet this requirement? So the meaning of the question is that there are different faults, right? Like there are 5 types of fault. And then based on those 5 faults, you are designing a nonlinear controller. For example, a fuzzy logic controller. But and there are few parameters in the controller. So how would you tune? Would you, and only one set of parameter is desired. And the control goal is that you find out only one optimal set that is desired. So therefore, how would you tune the parameters? The question is, would you when you start tuning the parameters, what will be your base? Would you start considering that there is 1LG fault or 2LG fault, 3LG fault, or 2LS fault? What will be your basis to
I
tune?
think I already start from the severe fault like 3LG.
Exactly.
Start from 1LG.
So who said from 1LG?
Lakshmi.
Okay, okay. And then Manoj, you said 3LG. Then there are other opinions?
I would say 3LG.
Okay. Also.
Yeah, it starts from the 3LG and then goes to 1LG.
Okay. So the thing is that now everybody see, definitely, like if you design for example, you consider the system has 3LG fault, then definitely you will get one set of parameter, right? And then next time you consider, okay, your fault is on 1LG, definitely you will get another set of parameter corresponding to that. And then 2LG, 2L, in each case, you will get one set of parameter. So this means if there are 5 set of parameters, then the system will run well. That is the common sense, general sense. But here the question is that only one set of parameter is desired. Meaning that I am telling that you pick up only one set, that time which set you would prefer? So Lakshmi, do you get it now? I am telling you.
Yes, doctor, I understood now. Yeah, mostly 3LG is
Yes,
better.
3LG. The reason is that if you choose 3LG, because that is the most severest, so when it is 2LS for 2LG, 1LG, that is fine. But if you design your system considering 1LG and you say, okay, this is my only parameter, when the fault is 1LG, that time that will perform the best, no problem. But if at that time fault is 3LG, 2LS, then that is not enough. That will be really the under control. But if you set the system based on 3LG and then whatever 1LG, 2LS, still that is under control, within control, because that is your maximum scenario, most severe situation. So that's why the answer is that when tuning the parameters and only one set of parameter is desired, I will be choosing, my base will be 3LG fault. That will be the answer. So how do you tune mean? You will be telling that I will consider the 3 as the fault as the standard or as the basis to start tuning the parameters. Everybody, could you follow me?
Yes, sir.
Yes, doctor.
Yeah. So therefore, that will be the answer, the 3LG fault. Okay. You see, I mean, because in this class we are learning the transient stability, so therefore I have set up different type of question and different way I am asking you to clarify your concept or the knowledge. That is the goal. That's why I that prefer in terms of the question, then it will clarify you much more. You don't take other way that, okay, I am asking you a lot of questions. So please don't take in that way. So this is for learning. That's why I have set up these questions. Okay, question number 3. In an industry, there is an induction generator, which is providing power to a grid. Okay, good. And then consider an unbalanced fault occurs on the transmission line of the network. So unbalanced fault means any of those faults like 1LG, 2LG or 2LS. Under such condition, why is reactive power control necessary? If you insert a parallel resistor at the generator terminal, will not the system be stable? Explain your answer. So, meaning that your system has that induction generator that is providing power, unbalanced fault happened, and then reactive power control is necessary. Why the reactive power control is necessary? Why cannot a parallel resistor at the generator terminal maintain the stability? So that parallel resistor means basically the braking resistor that we are learning. So if you insert a braking resistor, can it not stabilize the system? Why we have to control the reactive power? So
To maintain the power factor.
yes, so why the power factor maintain is needed? Why? That is the question. That reactive power control means power. That is right. Or your statement is right.
Yeah, yes, sir.
Why do you need that one? How did you decide that thing? By looking what?
In general sense, I have told, sir.
Because,
Yeah.
yeah, go ahead.
Yes, Manas, go ahead.
I think we already discussed this question before because
Yeah, before. Yes.
we don't have like AVR and other things in the induction generator. So there would be voltage, what do we call it? Voltage collapse.
Yes.
So the power, and that means like the torque would be directly proportional to voltage square. So in order to compensate that torque, it has to draw a lot of current from the grid. So for that, we have to, we need some kind of reactive power control.
Yes, yes,
to
exactly.
enhance the power factor. And
Exactly, right, right. So therefore, everybody see in the very first line, your generator is induction generator. That is not the synchronous machine. Because you have the induction generator, what is happening? Continuously it is taking reactive power from the grid. When that Manoj explained, continuously it is taking reactive power to produce magnetization. And that is causing the low lagging power factor. So that is even the normal situation during balanced case, during stable situation. So it is continuously drawing the reactive power for its operation, and then the fault happened. Whatever the fault is, unbalanced or balanced or whatever any of these fault happened, that will make the situation more worse. Generator will try to draw much more reactive power to recover or compensate that torque, electromagnetic torque. So consequently, there will be much more voltage sag, voltage drop, even voltage collapse might happen. That's why reactive power control is important. So therefore, main thing is that you will be telling, because this is the induction generator, always irrespective of the fault, always it is drawing reactive power from the system to produce its magnetization. And then, as Manoj said, in addition, it does not have AVR governor or anything. So that's why during fault situation, it goes much more worse. Its voltage go much more low. Voltage collapse might happen. That's why you have to control the reactive power, meaning that reactive support is needed. So this means you need capacitor or STATCOM or SBC or synchronous condenser. Those type of equipment is needed. So now the question is, if you insert a parallel resistor, which is a breaking resistor, will not the system be stable? System might not be stable, depending on the how much voltage goes down. It may work a little bit, but not full. That is not enough. In fact, if the voltage goes very low, voltage collapse happen, the answer is no, it cannot stabilize the system. So therefore, again, keep in mind that braking resistor or parallel resistor, that is for the synchronous generator stabilization, not for the induction generator.
So in this case, instead of the parallel resistor, we need to connect the capacitor in parallel, right?
Exactly. You have to
Yeah.
insert that. So therefore, reactive power control means basically connecting the capacitor or static Bird compensator or static synchronous compensator or synchronous condenser. I mean, the device, the flexible AC transmission device, FACTS device, those can control the reactive power. Therefore,
Facts devices.
yes, FACTS devices. So therefore, very basic, simple thing is the capacitor bank.
Sir, but in case of induction generator, if the fault currents are flowing, from where we are going to neutralize those faults?
The faults. So one,
In case
no,
if
so
there are fault currents entering into the system, so
yeah,
from where we are going to ground the faults? Like in case of synchronous generator, we are flowing the currents through the braking resistor, right?
yes.
So in case of induction generator,
So
we are using any component
and no,
to
so in
ground
this
those
case,
faults?
no, in this case, you see, already there is on capacitor connected at the terminal, right?
Yes.
Even at the steady state, already there is on capacitor. During fault condition, you need to provide additional controller, additional reactive controller, and typically you will be connected that at the grid point. And then you're in this case, it is not like that you will be making it grounding. Oh no, of course, you see, because this is connected to the grid, definitely you have the transformer, and transformer has the neutral connection. So therefore, because I mentioned unbalanced fault, certainly some zero sequence current is also developed. Not only just the normal fault current, positive sequence, zero sequence current will also develop. And those will be flowing, going to the ground through the neutral. Therefore, your generator will have neutral, your transformer will have neutral. So there are many paths of the neutral to go. But here the mechanism, reactive power control mechanism, is not through that neutral. Not you have to flow to the neutral. what you have to do? You have to insert the capacitor that will work against the inductive effect. So therefore, by improving the power factor, it will return back the voltage. The voltage will come back.
So
Then
that
the
is acting
system
as a compensation device, right?
no,
That is
there
what
is
you mean.
no compensation device here. So
But
no,
okay.
along the line of the network, this is connected to a grid, right? So therefore, along the line, already there is some protection means. For example, of course, the circuit breaker will work. There are regular interval voltage regulator. There are some voltage regulator along the line. Those will work. All the primary control means will work, like circuit breaker and voltage regulator. Those things will work. Protective relay will work. But still you have to put at the generator terminal some compensator. In this case, that compensator is the capacitor. So is this fine?
Yes, sir.
Okay. Now the next question is, what is an infinite bus? And assume several generators are providing power to a grid point. Under what condition can you add a new generator to that grid point, maintaining stability of the network? So first of all, what is the infinite bus? How would you answer this one?
So constant frequency and voltage, whatever the load fluctuation might be, there would be constant voltage and frequency.
Right. So therefore, for example, for every system, this is a system. Can you see the numbering like 21, 1, 2, 3? These are called the bus. So therefore, there are 30 bus. You see, this is the number 30. This is the number 1, 21, 2, 3 in that. If you count total, this is 30 bus. Therefore, among these buses, there can be one point in the system that will be the infinite bus, meaning that the voltage and frequency at that point is constant within a certain limit. If that limit violates, for example, during fault, power flow becomes very high at that point, that time the voltage and frequency of that point will change. Otherwise, voltage and frequency will not change. That's why it is called like infinite bus, like unlimited bus. That is the meaning. So therefore, sometimes in the literature, like the book that I am using, Prabha Kundra's book or any other power book, you will see sometimes it is called the slag bus, slag, SLC, or the reference bus. Reference bus or slag bus. It is the same meaning, or it is called the infinite bus. When you will be analyzing a power network, to calculate the power flow, to calculate active and reactive power, definitely you have to consider one of the buses in the system as infinite bus, meaning that that is your reference point, reference bus. And that is the reason, because that is your reference point, reference means the fixed. So that's why the voltage and frequency will not be changed, of course, within a certain limit. So therefore, infinite bus, in other words, a reference bus, a slag bus. Now, several generators are providing power to the grid. Under what condition can you add a new generator to that grid point, maintaining stability of the network? So therefore, for example, this is a system. Now all generators are connected, you see. Now think about just one generator. I think the voltage are not maintained, but the voltage of these generators are at least 13.8 kV, around that range, 13.8 kV. Now the question is, what is the condition that you can connect a new generator at that bus? What will be the condition? What you will check? That is the meaning of the question. It may happen for any of the generator. There is a generator, you want to connect a generator at this point, another generator. So what is that condition? What you will check? The
Synchronism.
Synchronism, right. So therefore, for example, as I said, if it has the 11 kV or 13 kV, then the generator that you want to connect, that should also have the same voltage. There should not be any voltage difference. Then you cannot connect. If there is voltage difference, then what will happen? There will be some circulating current flow. There will be some power exchange between these two generators. And then those two generators will be gradually heated up. Rather than contributing power towards the network, they will start exchanging power because there is voltage difference. You see, what is the condition of current flow between 2 points? If there is voltage difference, right? If there is potential difference. So that's why when you will be connecting a new generator with an existing, you must make sure that they have the same voltage. Also, what you will check, you make sure that they have the same frequency. For example, this is 60 hertz. Now, if you connect a 50 hertz generator, then that will also cause problem. Again, both generators might be heated up because there will be some circulating current flow. Also, their phase sequence must be the same. Phase sequence means ABC. The new generator should also have the same phase sequence, ABC. So therefore, those are the conditions that their voltage should be same, their frequency should be same, their phase sequence should be the same. Everybody, could you follow me?
Yes, Dr.
So Venkat, is this fine? Hello, Venkat. I think he left.
Yes, sir.
Oh, okay. So do you understand the answers of this one?
Yeah, yes.
Yes, yes. Like you have to maintain certain condition. The first condition, voltage, and then frequency, also the phase sequence. Otherwise, you cannot connect a new generator to the system. That will cause the stability problem. So that's why I said, to that grid point, maintaining stability of the network, so that you don't hamper, you don't break the stability or the synchronism of the system. You have to be very careful in connecting a new generator to the grid point. Are you all noting down the answers?
Yeah, yes, sir.
Okay. Okay. Now everybody see the next question, like question and question, the question bank. Now everybody see this picture. The first read the question. Consider in the following closed loop control braking registered system, the calculation of TKED is failed or significantly delayed. Will there be any effect on system stability? Now everybody see, in this picture, I was explaining you that your TK is your input, controller input. And I have defined here, what is TKED? W total at transient state minus W total at steady state. This means that to provide that input to the controller, you must need to know what is your W total. So that's why this figure shows that thing. Here is your braking register. You see, thyristor switch in the nth braking circuit. And that is your, you see, fuzzy logic or PI controller. Just an example. It is giving the alpha firing angle, and then its input is TKED. Now, how you do calculate the TKED? That's why I'm assuming there is a master computer, which is called like central control system. That is calculating the TKED. So how to calculate the TKED? This is that process. Everybody see, there are 10 generators like G1, G2, G3. I'm assuming that, okay, this is the power meter. And then to calculate TKED, what you need? Everybody see, we were discussing, look this equation, you need to have Ji omega m square. So Ji is the moment of inertia that will come from this equation that is fixed. Every generator has its particular rating and every generator has a defined prescribed H value. So therefore this factor is constant. Only variable is your omega m. What is omega m? That is your angular velocity in radian per second. So now you need to capture that speed information, angular velocity. That's why from every generator you see speed signal is coming. And then at first they are processed through filter. Why the filter is used? To remove any noise, to remove any impurity, to remove any oscillation or the ripple in those analog signal. So keep in mind that these speed signal are the analog signal. And then after passing through filter, they are processed, they are sent to analog to digital converter, AD converter, analog to digital. And then here it is digitalized signal. And then you see, can you see this antenna? Here I am using that GPS process, global positioning system. The GPS that you use in your car, exactly the same GPS. So why I am doing that one? Because once I get the signal at GPS receiver, it can make the signal both time and phase synchronized. And then that synchronized signal is going to the centralized controller, central control office, master computer, where by using that equation, you see, that kinetic energy is calculated and then summed up for all 10 generators. Now the thing is that because you see, those generators are not located at the same place. I mean, here in the picture, I have put them all in online. Horizontally, I have put. But if you see the real structure or just this example, you see one is here, other one is here. And can you see the distance? 100, 100, so like 1, 2, 3, 4, 5, 6, 7, 8, 9. 1000 kilometer distance from G1 and G2. And then also there is distance. So from this point to this point. Now your controller, if your controller is here, then you will be collecting signal from each generator. They are not equidistant. They are not located at the same distance. If you put controller here, then this generator is closest. If you put controller here, this generator is closest, but other generator are far away. So that is the reason what you have to do. You have to take the help of GPS. That will make your collected digitalized speed signals into time and phase synchronized. And that is the function of the GPS. So that there is no time delay. Because GPS accuracy in North America, 1 microsecond, 1 to 2 microsecond accuracy. The GPS that you use in car, and same thing is true for power grid. So therefore, only with 1 or 2 microsecond delay, it can provide you the time and phase synchronized signal. So that's why this arrangement is used just to collect the speed signal. And then in the central control office, you have your algorithm, you have your code, for example, to calculate this one, you have the calculation process. Once you get the omega m, then you are ready to calculate, and then you make the difference. That is your TKD, that is going controller. Controller is operating the braking resistor, and then braking resistor is effect is going to the network. That's why this is a closed loop system. That is the meaning. Now come back to the question. Consider in the following closed loop control braking resistor. The whole purpose is the controlling that braking resistor. The calculation of TK is failed or significantly delayed. Will there be any effect on the system stability? So you see, it's complicated process. Now it might happen that TKED is failed. The central control office, master computer, did not get the signal properly, either because of it is significantly delayed or somehow failed, like communication failed. Then will there have any impact on the system stability? What do you think?
Yes.
Yes, definitely. Because if you see that this controller, master computer or master controller cannot get the signal properly, or it cannot, or it failed, whatever, then the signal is not going to your controller. For example, your controller is ready to operate. Your braking register is ready to operate, but it is not getting the signal properly, either because it failed or because significantly delayed, like 2 second, 3 second delayed. So in the digital age, modern age, 1 second, 2 second is too big. If it is microsecond range, then that is okay. But if it is significantly delayed, like more than 1 second at least, then the system stability may hamper. By then, because your goal is, once there is fault, your goal is to quickly operate this braking register. You have to quickly send the alpha signal Now this is your TKED, you know, total kinetic energy. I mean, here I have seen the flow from this generator just to understand, but in fact that TK is coming from all generators. So therefore, if there is no input, how it will produce in a timely manner the output? Consequently, the performance of the braking register will be affected. I mean, before processing it, by then there will be a lot of device damage in the system. Even though the braking register, even though the protective relay work, but if it is well delayed, then system stability might not come back. The oscillation will go on. So therefore, everybody see the answer to this question, that if the calculation of TKG failed or significantly delayed, so there will be impact on the system stability. System might be unstable, or the system response might be oscillating. That will be damaging or detrimental for the connected devices and connected system. Everybody, could you follow me?
Yes, Dr.
Yes,
Ali.
sir.
Yes. Okay. So now further moving forward, much more question. Everybody read number 6. Assume a 3-phase to ground fault occurs in a power network, and consequently the system stability gets affected. That is for sure, that will happen. Okay, then you use the thyristor system, thyristor switch dynamic braking resistor, the braking resistor that we are discussing, to maintain the transient stability. That is fine. Now what I am asking, is there any negative consequence of using the switched braking resistor in the power network? Explain your answer. So like so far, always I talk positively. Always I am in favor of the braking resistor in case of the synchronous generator, and the fault happened, and this is the severest fault. System stability got affected, and then I connected braking resistor. It maintained the system stability. But in between, in the meantime, could there be any negative impact of using the braking resistor in the power network? Can you guess that there could be any effect on any of the component?
I'm not sure if consuming the power will be bad for the system, because the resistor always needs to consume powers.
So therefore, which bad? That is right. Which what is bad? I mean, which
Because
component will be affected?
which component will be affected?
So, for example, generator has shaft, right? So, do you
Yes.
think that there can be any impact on the shaft system because the thyristor switch is happening? So, I mean, everybody see, what is the reason of asking that question? Everybody, 1 second, you come back here. This is thyristor, right? You are sending the pulse signal. You are sending the triggering signal. Like kind of, you are controlling the current. Like kind of the switching happening. You are controlling the current means you are controlling the power consumption. Therefore, think about that. I mean, let me take you to that just a moment, to that whiteboard, then you get it, what I am asking. So Aman, just a moment. This is your generator. And you see, this is your shaft system. Okay, and then here are the loads connected. Just a simple schematic. And for example, here the fault happened somewhere. That is the fault point F. And then your braking register is here. Just I'm briefly drawing. So this is your BR, braking register. And then let me write down that equation. You see, every day we talk, or I talk about that swing equation, because without that, we cannot explain the phenomena of synchronous generator. This is my swing equation. Now, and then this is the shaft. And here is that FM, mechanical power, and here is that electrical power, right? So now, like Amani, look,
Mhm.
we are controlling this braking resistor, right?
Yes.
I mean, with the help that firing angle, with the help of the alpha, assume that there is thyristor circuit here. Now, what we are controlling? What is our goal? That during fault, because P goes very low, I mean, it goes like close to 0, that you support the with the help of the braking resistor, meaning that you try to increase that phi from the 0 to maintain the stability. So meaning that each time you are sending the alpha to the thyristor, your power consumption through the braking resistor is changing. Meaning that you are continuously controlling, with the switch, through the switch, you are continuously changing your phi. Sometimes 100 megawatt, sometimes 98 megawatt, 90 megawatt, because you are controlling the current flow here by controlling the alpha value. And that is happening like every millisecond or microsecond rate. So therefore, each time what is happening, we are assuming that initially it has constant value, but then generator speed got disturbed. Like it will start spinning faster, right? It will be the response of the speed. If you look the speed profile, over the time, then it will go high and then it will oscillate until it is fixed. So therefore, in one hand, the oscillation is going on. On the other hand, you see, you are injecting the power here. Every microsecond or every millisecond, you are controlling this alpha. Consequently, it is providing different power. Accordingly, here this number is continuously getting like plus minus. It is changing. So therefore, that is causing some vibration on the shaft system. So therefore, ultimately your shaft system might be affected somewhat because of those type of continuous, the fluctuation or continuous power provide. On the other hand, if you had just only one switch, for example, you remember the traditional system is that if you have a switch, so during fault you just connect, and then when there is no fault, you just take it out. This means this is just one operation. That time it will have the less impact. But you see, we discussed that there are a lot of problems of this. This is conservative because only one operation. That's why we have chosen fuzzy control thyristor switch, and that is the preferred that we understand and that is needed. But what is happening? Because I am controlling with the help of the alpha, therefore continuously there is switching. This power is continuously changing. And then that is causing some oscillation. It is kind of like vibrating until it is fixed. So sometimes there are some, why I am bringing this point, there are some example that the shaft system has been cracked or is somewhat broken or deformed, that shaft system. So therefore the impact will go on the shaft system. That is the negative thing of this method. Otherwise everything is positive. So everybody, could you follow me?
Yes, sir.
Sir.
Yeah. So the impact will go on the shaft system because really you look this equation, PM is your mechanical power, P is your that you are controlling, and then P is called the accelerating power. So therefore, continuously like you are changing that acceleration amount. So there will be vibration, and at some point there might be deformation or crack or some damage or breakage, etc. Okay, so therefore now moving forward to that question. Now see, so now once again everybody say the question is there any negative consequence of using the switched braking resistor in the power network? The answer is yes. There might be negative consequence or negative impact on the shaft system, connected shaft system, because of continuous switching the braking resistor. Although the transient stability will be maintained, system might not be unstable, but because of the continuous vibration or oscillation, there might be some blockage or damage or deformation of the shaft system. Okay, now then moving forward, in continuation to that question, the next question, to mitigate the shaft oscillation of turbine-driven synchronous generator system in a power network, it is desired to design a controller. Which of the following variable should be used as the controller input? Explain your answer. Now you see the question is, turbine driven mean steam turbine, gas turbine, nuclear turbine, that is the meaning, big size of generator, and there is shaft oscillation. That thing I explained. Now you need to design a controller to mitigate, to suppress those shaft oscillation. Now which of the following variable you should use for the controller? Is it generator terminal voltage, or generator speed, or power factor, or system total reactance? Which parameter you will consider as the input in this case?
I think generator speed.
Yeah, generator
Generator speed, right?
and system total reactance.
Yeah,
And the last one.
yes, so therefore system total reactance, if you consider, that will control the reactive power. So in this case, you see, because the issue is mainly with the oscillation is related to that frequency. So therefore, right, so therefore appropriate answer would be generator speed. I mean, definitely it will help somewhat system total reactance, but total reactance will control the reactive power. So that's why even I am not choosing the power factor, or even I am not choosing the terminal voltage, because number 1, number 3, number 4 are like interrelated. Those are kind of reactive power compensator. Therefore, it will help somewhat. I mean, Kamana, you are right, somewhat, but the appropriate answer would be generator speed. So therefore, everybody please write down that the appropriate input to the controller would be generator speed, because the issue is with the shaft oscillation, and shaft oscillation means your speed oscillation. Speed is like going high, going low, and ultimately causing the frequency oscillation. Everybody, so could you follow me?
Yes, sir.
So
Yes.
did you all, Lakshmi, Sindhuja, did you write down the answer?
Yes, Dr. Ali.
Yes, Dr. Ali.
Okay, very good. Now come back the next question. A fuzzy logic controller is not able to capture the history of the control variables, while a conventional PID controller is able to do that. PID means proportional integral derivative. Then what is the specific feature of a fuzzy logic controller so that power engineers are motivated to use it? I mean, for example, here I said fuzzy logic controller, or in this example, I said, I mean, in the literature, you will see a lot of application, fuzzy logic controller for braking resistor. So what is the motivation behind that? And I said, you see this thing, fuzzy logic controller is not able to capture the history of the control variables, while a conventional controller can do that. So has anybody applied any fuzzy logic controller for any application? I mean, even though in your undergrad study, has anybody applied? For anything, I mean, not necessarily the power grid application, for anything, have you used? Or have you used the PI or PID controller? For anything, like for any project or for anything, even in your undergraduate?
No, sir.
Okay. Now, why I'm asking this question, because I have said some specific thing that fuzzy logic controller is not able to capture the history of the control variables. So meaning that for this type of controller, fuzzy logic controller does not have any memory. It cannot save the history. It continuously gets the input and then immediately release the output. It does not have that capability. Because it is not dependent on any time derivative or integration. It does not have those capability. It cannot make d by dt, or it cannot make integration. So meaning it is just a simple nonlinear controller. Just it is based on the simple arithmetic. It is not based on a calculus or even the advanced math. But it is a very good example of nonlinear controller, and that works well. On the other hand, if you use the PID, proportional, integral, and derivative controller, which is the question here, then that is able to capture the history. You see why I am saying? Because PID means proportional, integral, derivative. Proportional is proportional, this is constant, but integration, it is making integration like over the time. And D means derivative. So this means when you are using a PID controller for any system, I mean, not necessarily the braking register, for anything, even in any other courses, any other subject, that is able to capture the history. So therefore, is it not better that you can choose a controller that is able to capture the history because it has the integral capability and derivative capability? So that's why the question is coming. A fuzzy logic controller is not able to capture the history because it is just based on simple logic. If then, it is based on if then. Like if there is a lot of cold outside, then I will not go outside. If it is too much hot, then I will not go outside. That is the meaning of the fuzzy logic controller. It is simply based on arithmetic and if-then logic, which is called fuzzy rule. On the other hand, conventional controller, it is fully dependent on derivative factor and integration factor. Like you are integrating over the time. Definitely it is capturing the information, the past time and current time, and then of course the future time.
So that means this PID controller has time delay, and that fuzzy doesn't have that much time delay.
Exactly, because it is independent of those functions. Therefore, it is not capturing history. You don't need to capture the history. If it is like problem is about your, what is called, like artificial intelligence something, or selection, optimization something, that time you need the history of information. Otherwise, you don't need, because you will be applying your controller only for transient moment. Your goal is to stabilize the system as quickly as possible. So that's why you don't need to look what is the history. Let it work quickly. Of course, PID controller will also work. I mean, in this case, if you use a PID, it will work. But it has been seen after a lot of trial and error that always a nonlinear controller, I mean, not necessarily fuzzy controller, there are other nonlinear controller like Lyapunov function controller, H infinity controller, sliding mode controller, variable structure controller. There are lots of nonlinear control structure. I mean, fuzzy logic is the simple one. That's why I have shown it here as an example, as a nonlinear controller. If you use PID, still the system will work, but like as Manoj mentioned, there can be some more delay because there is derivative factor and there is integral factor. That's why always it has been noticed that the fuzzy controller work better than the PID controller, even though it cannot capture the history. That is the meaning of the question. So therefore, when the question is what is the specific feature of a fuzzy logic controller so that power engineers are motivated to use it, you will be telling that fuzzy logic controller is a nonlinear controller. And it is based on simple if-then rules. It is based on simple arithmetic, simple algebra. Even you don't need any trigonometry. You don't need any geometry. You don't need any calculus. If you really see the structure of fuzzy logic controller from any reference, any book, then you will see really it is based on, you need only 2 or 3 equations, algebraic equation to get the output. On the other hand, PID controller, you have to use integrator and differentiator. And that introduces some sort of delay and somewhat worse performance than the fuzzy logic controller. So therefore, you will be telling that the specific feature of fuzzy controller, that it can work well in nonlinear situation It can work in imprecise or uncertain situation. In addition, it is based on simple if-then rule, and it follows only the arithmetic function. That's why power engineers prefer it, or power engineers are motivated to use it. Everybody, could you follow me?
Yes, sir.
Okay.
Yes. So, or in other words, fuzzy logic is a nonlinear controller. PID is a kind of the linear controller. So, because it is the application of the power grid, keep in mind power grid, already we told, power grid is highly and highly nonlinear. There are lots of nonlinear components. A single inductance is nonlinear. Therefore, generator inside itself, you have it has the coil, stator coils, that is nonlinear. That's why the nonlinear controller always work better in power network. I mean, of course, PID will work, but if you apply both to any problem in power network, definitely you will see the nonlinear controller has superiority to the conventional PID controller. Okay, everybody say there is a numerical problem, and then I think we'll be done for today. Everybody read that problem and try to solve. Read it. A 60 Hertz, 11 kV, line-to-line RMS voltage, electrical grid supplies power to an industrial DC motor through a 6-pulse thyristor bridge rectifier under full conduction. In order to minimize harmonics and provide a stiff DC voltage, a capacitor of 2.5 megajoule capacity is connected at the terminal of the motor. Then calculate the required capacitor value. So therefore, everybody see. So therefore, let me draw a schematic for you, and then you can get it easily. Okay, so therefore, so you just draw the picture with me. You have that grid system, and that grid, this grid is going, and then there is a, you can draw with me in your note, and then I will go back to that problem. So this is that, let me write down. This is that 6-pulse bridge rectifier. This is that 6-pulse bridge rectifier, this body. And then from there, you see, definitely because this is bridge rectifier, it is producing DC. And that DC is powering a DC motor. So therefore, this is your DC motor here. This is DC motor. And then it says, statement says that there is a capacitor here. This is that capacitor. This capacitor is used so that the DC motor gets smooth DC. Because your this side is AC, for example, this is A phase, this is B phase, this is C phase. Probably it was 11 kV here, it was mentioned, generator rating. And it has the 60 Hertz system. I think those two informations were given. And this is 6 pulse, and also it says full conduction. Full conduction means here your firing angle, alpha is 0 degree. Yes. So therefore, definitely you see this side it is the DC because it is the rectifier. So this side is AC and that side is DC. And there is a capacitor. And this is a DC motor. So everybody please draw this picture, and then I am taking you to that problem. Have you all drawn the picture in your paper?
Yes, Dr. Ali.
Okay, Lakshmi. Okay, Sindhuja, have you drawn?
Yes, doctor.
Okay. Manoj, Kamana, Amani, everybody.
Yes, Dr. Ali.
Yes, Dr. Ali.
Yes, actually.
Venkat.
Yes, sir.
Okay. Now I am going to that problem. Now this is your diagram. Now look this one. Now read this one. A 60 Hertz 11 kV line to line RMS electric grid. This means the leftmost component supplies power to an industrial DC motor through a 6-pulse bridge rectifier under full conduction. This under full conduction means firing angle alpha is 0 degree. Now, in order to minimize harmonics and to provide a step DC voltage, a capacitor of 2.5 megajoule capacity is connected at the terminal. That is that capacitor. So therefore, now in your note, you write down this capacity 2.5 megajoule, that capacitor capacity, energy storage capacity. And then you already wrote down those two information on the grid side. Now, based on this information, what should be the required capacitor value? What is the capacitor value that you have to do?
Is it 0.023 farad?
0.023
3
farad.
farad.
Yes, that is right. Yeah. So everybody, could you guess what to do? Therefore, you see, actually for you, I have done this one. You see that picture. So what you have to do? You have this information, AC RMS voltage 11 kV. So first you calculate what is the DC voltage available here. What is your VC or the VDC? So you see before we have used this equation, 3 Vm by pi cosine of alpha. And keep in mind that Vm is peak to peak RMS voltage. So that's why this 11 kV multiplied by root 2 and then cosine 0 degree. So you are getting 14.86 kV. You might express in volt. And then what is the energy storage equation across capacitor? That is half C Vc square. Vc is the capacitor voltage. That is 2.5 megajoule, which is given. And then from there you calculate the C. You multiply 2 here and then divide by Vc square. This means this voltage. Then this is farad, just I expressed in millifarad, 22.64 millifarad, or that Manoj said 0.0264 farad. Everybody, could you follow this one?
Yes, Dr. Ali.
Yes.
Yes, sir.
Yeah. And Sindhuja, are you fine?
Yes, Dr. Ali.
So therefore just I did and then you calculate. So you should be getting this. Either you express millifarad or farad, that does not matter. Okay, so with that, I like to stop here. Does anybody have any question?
No question, Dr. Ali.
Okay, so therefore I am stop sharing this one.